Okay, today we're going to talk about one-way analysis of variance, one-way ANOVA, or, let me write that down, sometimes it's called completely randomized design. Either one of them refers to the same thing. Completely randomized design. What is it for? Why do we do it? Okay, so we know that we start out with one population at a time. We did that first, one. And we can use Z's or T's to test that. Then we worked up to two populations at a time. We use Z's and T's. Now what if we want to have more than two? Let's say we want to have K populations, or really we're testing the impact of K treatments on a population. All right, so when you do this, you're saying, all right, I've got this population and I'm imposing some treatment on it. What's going on? So I've got all my little things that look like everything else that I draw. Now, I can't use Z's and T's anymore. I have to use something called the F distribution. And you're saying F, what does that stand for? Don't go for the obvious. It actually is in honor of Sir Ronald Fisher, who is the father of modern statistics. And we'll talk a little bit about that in a minute. So what we're doing is actually taking K populations and imposing treatments on them, if you will, and testing the means based on those treatments. So we talk about equality of treatment means. That's what we're saying, okay? I have K populations or K treatments. It's the same thing. Each population gets one treatment, okay? And we're testing to see if the means after the treatment are equal. All right? Let's look at a little numeric example. And we're going to work, and it's a little tedious, but I think you'll have a better feel for it. I found this and kind of doctored it up a little bit. They're doing some kind of testing for vitamins on some kind of little creatures. I don't like little creatures, rats or mice or something. Let me copy all the numbers. Just hang on a minute. 54, finally 44, 52, and 63. So in data set 1 I have 3 observations, 52, 56, and 54. If I add them up, I get 162. And that's my total 1, so that's T1 equal to 162. Then T2, my total from the second column, is 174. And T3 is 159. Now if I add up all the observations or add up all the totals, the grand total, the T with no subscript, is 495. And that's just the total of the whole set of observations. Okay? Then the N for each one, that is how many observations in each sample. Okay, N1 is 3, N2 is 3, N3 is 3, nothing very exciting there. And then N with no subscript is 9. How many total observations are there? 9. Okay, now let's look at a sample mean for each column. So X bar 1 is going to be 162 over 3, which is 54. And x bar 2 is 174 over 3, which is 58. And x bar 3 is 159 over 3, which is 53. And the grand total is going to be the x double bar is the 495 over 9. So it's the grand total of t, 495, divided by 9. And that's equal to, where'd it go, 55. Okay? Now, the next thing I'm going to do is get square values of each observation. So I'm going to take 52 squared plus 56 squared plus 54 squared. I'm just going to call that x1 squared. It's actually the total from the row. So 52 squared plus 56 squared plus 54 squared is equal to 8756. And then the second one, if I take 63 squared plus 57 squared plus 54 squared, my dog just snored. I don't know if you can hear it. 10134. And then finally, from the third one, there she goes, 8609. Then the important one, the one you really need to know, is the grand total, the summation of the x's squared, and that's 27499, and we're going to use that a lot. Let me write it here, 27499. Okay? So these are the values that we're going to use all the time. All right. So the next thing we have to do is constructing our sums of squares and our table. So we need to get our treatment sum of squares, and that's going to be t1 squared over n1 plus t2 squared over n2 plus t3 squared over n3 minus t with no subscript squared over n with no subscript. So you do however many t's, little t's there are, and then subtract out the grand T. So we're going to have 162 squared over 3 plus 174 squared over 3 plus 159 squared over 3 minus 495 squared over 9. Okay? So then you're going to have 8748 plus 10092 plus 8427 minus 27225. And that's going to give me 42. Good. All right, then the total sum of squares, the SST, is going to be the summation of the xi squared minus the t squared over n. And you'll subtract out the same thing that you got before. So you're going to have the 27499 that we had at the end of the last page minus that 27225 And before you know it, you will have, where did you go? 274. Okay? All right. Now the SSE, the error sum of squares, you take that 274 and subtract out the 42. And before you can say design of experiments, you have 232. All right. Let's put together a generic ANOVA table, and then we'll fill in the correct numbers. So the generic table looks like this for one-way ANOVA. You have source, degrees of freedom, sum of squares, mean square, and F. So you have treatment, you have K minus 1, you have treatment sum of squares, you have mean square treatment, and you have F star. Okay? Then you have error, then you have N minus K, you have SSE, then you have mean square error, and then you have total, and then you have N minus 1, and then you have SST. Okay? So that's the generic one, and we've seen so far how to get the first two columns, that is the degrees of freedom and the sum of squares column. All right, so our next trick is going to be how to fill in the mean squares and the F star. All right. So to get the mean squared treatment is sum of squares treatment divided by treatment degrees of freedom. Simple as that. Similarly, mean square error is sum of squares error divided by error degrees of freedom. Yay! And finally, the F star is mean square treatment over mean square error. And then we'll do the hypothesis test in a couple minutes. All right? So let's start putting this puppy together and see what we come up with. So let's change our slide out. So we'll have source. Oh, my pen's getting funky. Sum of squares, mean squares, F. Treatment. So we had 21 here. Error. We had 232 total. And that is 274. Okay, so treatment degrees of freedom are K minus 1 in this case. So K is the number of treatments. Oops. K, let me erase that. K is the number of treatments. How many treatments did we have? We had 3. That's number. So 3 minus 1 is 2. Now the way I like to do this is kind of go at it backwards. I know the total observation is 9, so 9 minus 1 is 8. Therefore, these two columns, the degrees of freedom and the sum of squares, are additive. So once you've got 2, you've got the third one, either by addition or subtraction. Therefore, the error degrees of freedom must be 6. I changed colors. All right. Now I need to get my mean square, and I'm going to have, I put the wrong numbers in. Sorry about that. I was one step ahead. Okay, that's 42. All right, so then my mean square treatment is going to be 42 over 2, which is 21. And my mean square error is 232 divided by 6. And that's going to be 38.667. And then F star, which gives me my test statistic, is 21. Sorry. I'm looking at my paper where my numbers are while I'm doing this. So I have 21 divided by 38.667, and I get 0.54. Isn't this fun? Okay, let's do the test statistic, hypothesis test. So just in case you thought this wasn't enough fun, what we're going to do is say mu1 is equal to mu2 is equal to mu3 versus not all mu sub I are equal. Okay. And our test statistic is the F star, that 0.54. Now you need to look up F at alpha with treatment degrees of freedom and error degrees of freedom. So I actually used F at 0.5 with 2 and 6 degrees of freedom, and I got 5.14. I cheated and I used R. So my if then is going to be if F star is greater than 5.14, then we reject HO. And we will fail to reject. Okay. Good times. Hope this helps.